Let's look at the deployment of fuel cells. We see that they're deployed at industry. There it is, along with gas turbines, in hotels, along with diesel engines and gas turbines. Also here at wastewater treatment plants. We're starting to see the deployment through ClearEdge, it was mentioned earlier today, and Plug Power at homes. And then we are going to see this next year of the deployment by utilities, both PG&E and Edison, to help support the distribution system. Those advanced technologies for central plant look very promising, but they're going to be 20, 25 years away before they're fully deployed. But they're well in progress with General Electric and Siemens and Rolls-Royce and others. If you look at this plot, we've talked a bit about today about the solar energy, right? That is giving rise to a paradigm change in the production of electricity at the endpoint of use. Also out in the transmission area. This has this diurnal variation, but it also has what we call an instantaneous intermittency, like a cloud going over. And as we increase the percentage, that's going to destabilize, and already is in some cases, destabilizing circuits in California. Fuel cells are an integral part of providing the buffer to that, There's another perturbation in this space, and that's right here. Barely see it. Little wire going into the house. Moves to the business, a little wire going into the business. And we've been talking about that today with respect to the plug-in vehicle. We see them outside. Bigger battery, plug it in, call it a plug-in. It's really a dual fuel vehicle. We've seen Brian Olson present about the Fisker. We have the Chevy Volt, and we have Toyota and other OEMs coming out with this vehicle here in the next year. I want you to also keep in mind that this is the platform for the hydrogen fuel cell vehicle. Bring in gasoline, or take it away, bring in hydrogen fuel cell, and this is what you should expect for the future along with BEVs, is the plug-in hydrogen fuel cell vehicle. Coming back to this plot, here's the disturbance of plug-in, disturbing the grid. We've got the solar disturbing the grid. And we heard Mayor Polito talk about the role of storage, electric storage in the distribution, electric storage in the transmission, electric storage in the home. What this gives rise to is management, and this is part of the smart grid future, is management. And there's 4 levels I want to introduce you to. There's the consumer level, which would be the homes, the office buildings, and the industry. There's the whole management of smart grid with respect to the electric vehicle. There's the utility control over the instability of the distribution circuit. And with respect to the transmission, there's the role of the utility as well as CAISO in having access to that smart grid technology. Here in Irvine, there's a platform being established. Here it is, a little hard to see in this early schematic, called the Irvine Smart Grid Demonstration Project. It's a remarkable project, actually, with Edison as the prime. It takes off from the MacArthur Station at Jamboree and Bison and involves 2 circuits, an existing circuit, the Rommel circuit, and a new circuit just now being installed, the Arnold circuit. Both of these would be made smart in a variety of ways, but one way would be through what's called a universal remote control interface. Also, here's the electrical storage that we moved along the circuits to see where it benefits the circuit the most. About 40 homes will be deployed with smart technologies. Block 1, called Zero Net. Block 2 will have home storage, meaning the battery will be at the home. Block 3 will have the battery at the transformer. And then, of course, there will be a control set as well. The homes will be outfitted with photovoltaic, with smart appliances, with, of course, smart meter, charge in the garage, electric vehicle, and other attributes to be able to evaluate this smart grid future. Here's a living laboratory in Irvine, $40 million project, stimulus funding, DOE. And there will be a training demonstration center located at the University Research Park. Let me conclude by simply identifying to you briefly two very interesting synergisms that fuel cells provide because they're not constrained by the heat engine Carnot cycle. The first one is coming back to our gas turbine engine here producing electricity. If we take out the combustion and replace it with a fuel cell, there's a synergism because we release the Carnot efficiency that gives rise to very high fuel to electrical conversion efficiencies that we're expecting to reach by the end of this decade, 70 and into the 70+%, maybe 75%. This is called hybrid fuel cell gas turbine technology. Where it pencils out on this chart of efficiency versus power plant capacity, where here we have a home, here we have a hotel, here we have a university or wastewater treatment plant, here we have a central plant, is the plot of gas turbines. And you can see the gas turbine technology that the efficiency increases as we go up in size. But there's that Carnot efficiency limit that we can't get over, 65% right there. Here's where the hybrid pencils out today. Here's where we see it tomorrow and in about 10 years up here. Not only increasing in fuel to electrical conversion efficiency, but in the breadth of application from distributed to central plant. The alpha test 2003, the first commercialization by Fuel Cell Energy in 2007, and then the artist rendering of what Rolls-Royce will be deploying in the next 2 years, this being at a 1 megawatt scale. Zero emission of criteria pollutants, no noise. There you see the application. There you see an application. Very, very nice application here. And frankly, this has to be hybrid technology in order to reach our environmental and efficiency goals. The final synergism is associated with a high temperature fuel cell that you now understand takes natural gas, produces AC power, and a thermal output. If we wish to extract something out of that, we can do so. But here's the evidence that that technology is being deployed today. The item that I'd like to extract out of that on demand is hydrogen for transportation. And here I've done it. It turns out that when you do that, there's a synergism that gives rise to a very interesting efficiency. I need to demonstrate that to you by giving 100 megajoules of natural gas to the fuel cell, producing 47 megajoules of electricity and 53 megajoules of heat. Now, if I increase this to 143 megajoules, I can tri-generate with hydrogen. I'm able to maintain the amount of electricity, to maintain the amount of waste heat, but I'm in addition able to extract hydrogen from this fuel cell at very close to 100% efficiency. It's about 103%. But it's due to a synergism with fuel cells, much like we saw with a hybrid. It's only governed by the NERTS potential. What's the application of this? Well, natural gas or biogas. If we do biogas, this becomes biohydrogen. Where might that be available? In a digester. Where might that be available? In a wastewater treatment plant, which today uses a boiler to provide heat for the digester. What we can do is replace that boiler with a fuel cell, use the heat to support the digester, and then produce electrical power at about 50% fuel to electrical conversion efficiency. About 8 megawatts of this delivered today in California. If I now, on demand, that's an example, generate biohydrogen, then I've got that extra product at no cost. This is actually a demonstration at the Orange County Sanitation District due to be commissioned in December of 2010. The fuel cell is on site, supported by the Department of Energy, Air Resources Board, and the AQMD. Kind of the epitome of sustainability, taking human waste and creating renewable electricity, renewable heat, and renewable transportation fuel. It's a strategic alliance, which most of our programs are, in this case with Air Products and Fuel Cell Energy. So the parting slide is this slide where now we can add the generation of hydrogen from biogas with a zero CO2 signature. Thank you.